Hello, this is Group 7, and we're going to talk about differential equations in clinical medicine. My name is Tom.
My name is Yunpo.
My name is Ethan Pereira.
My name is Moen.
So, mechanical ventilation is a life support therapy used when patients cannot breathe effectively on their own. So, its development spans from early artificial respiration concepts associated with Andreas Vesalius to up to the negative pressure iron lung of the polio era and the positive pressure ventilators used in what we call modern intensive care. So clinically, mechanical ventilation is used in the management of acute respiratory failure and severe COPD exacerbations and also other conditions that impair gas exchange. So this project is going to review and study how the ventilatory process can be represented mathematically using differential equations and mathematical modeling. Let's, here is an illustration of basically how a mechanical ventilator works, basically pumping air in and subtracting air out. Next page. So the history of mechanical ventilation goes back much further than modern hospitals and modern medicine. So we start with Andrea Vesalius in the 1500s when he basically showed that breathing could be sort of artificially supported by inflating the lungs. And that early idea was very important because it introduced the basic principle that respiration uh, could be assisted mechanically rather than left entirely to spontaneous breathing. And over the centuries, physicians and inventors explored like different methods for artificial respiration, but overall these efforts were still limited and not yet the practical ventilators used in medicine nowadays. And a major turning point came in the 20th century with the development of negative pressure ventilators, especially the iron lung, which was created by Philip Drinker and Louis Shaw. And these machines, they became especially important during the polio epidemics of the 1940s and 1950s, and when the patients lost the ability to breathe because of respiratory muscle paralysis. And later, medicine shifted from negative pressure systems to the positive pressures ventilators that are nowadays used. Next slide. So, in the clinical importance and why mechanical ventilation matters is because it is one of the most important life support interventions in modern medicine, and it is used when a patient basically cannot maintain adequate breathing independently, especially in cases of acute respiratory failure or hypoxemia, also in impaired ventilation or airway compromise. And in practical terms, the ventilator helps the body continue the two essential functions of respiration, which is bringing oxygen into the lungs and removing carbon dioxide from the blood. And why do we need the differential equations, which basically is how the breathing changes over time, and we are going to consider the variables of pressure, airflow, and volume. And the model will basically help connect physiology to measurable parameters.
In our project, we're using a single compartment mechanical system, and we're using the pressure balance equation, where PR will be the resisted pressure, and it can be found using the change of volume with respect to time, and using the R as a proportionality constant, which is a resistance of airway. And we can also find the PE, which would be the land elastic pressure, and C would be the compliance of the blunt. And since it is a compliance that will be inversely proportional to pressure, because with the high compliance, that will result in lower pressure for the same volume, as it is easier for the land to inflate. And we're also using the first order linear ordinary differential equation, because we know that it is going to be first order because of the derivative that we're going to use is the highest one is the first derivative. That's why we're using that equation. And also we can find we're using the elastic pressure as our linear function of volume. And we will be going to the another slides. So in here, during the inspiration phase, like we're using constant pressure from the ventilator, which we're being provided. So in order for us to solve that, we use the standard form of dy over dx plus p of x times y equal to q of x, and we want to change and convert our equation into that standard form. Now we can find the integrating factor. So when we find the integrating factor, we get e power t over rc. Why in here, the thing that we are keeping constant is p of t is equal to 1 over rc, and q of t is p of minus p of ex over r. And now, since we already got everything, we also got the integrating factor. We can now multiply that integrating factor on both sides, and that's how we would get the v of t is equal the function for the inspiration. And the earlier that we already got is a format that we can use for both of the inspiration and expiration. But in here, since we are trying to find the inspiration first, we need to think about when the time is equal to 0. At the start, land volume is 0, since we are trying to inspire the air. So the volume is 0 at first, and then we can substitute those numbers into our equations, and then we get C1. When in C1 in here means that in the earlier one, that is supposed to be the earlier slides in here, where C1 is equal to C times e power minus t over RC, and we just represent that by using C1. And then now we got C1, so we can substitute that back into our original function, and that's how we would get the v of t is equal to p up minus p ex times c times 1 minus e power negative t over rc, which is an exponential growth function. And which makes sense because as this time increases, our volume is going to be increasing. So now we got to expiration part. So we can, when the machine pressure PAW is like removed, because since it is like equal to 0, because, and also it is also like the expiration phase, so the air is going out, so we can use a separable ordinary differential equation, and then using the same format again as we use in the inspiration phase, we can now find the integrating factor again, which is the same, and do the same thing again in here. And now we got v of t is equal to negative cp ex plus c times e power negative t over rc. And now we can use initial value problems, theorems in which time is equal to Ti, which is the inspiration time, and V is going to be the Vt, which would be the tidal volume. And now we can, since we already solved C, we can substitute that back into our original function using that value that we already have. And now we get to V of t is equal to tidal volume times e power t inspiration minus t over RC, which is the exponential decay function, because as the times go on, now we kind of like breathe out, so the volume will be decreasing.
Here is our analytical result for our land volume model. During this inspiration, the land volume increased over time following an exponential function. This means the volume raises quickly at first and then gradually levels off. During expiration, the volume decreases exponentially from its maximum value, so both phases show the exponential behavior. And the key parameter here is the time constant RC, which controls how fast the land fills and empties. And can you go back to the previous slide? And the graph here is basically show the respiratory system air flows into the land and cause expansion, and which is what our equation is modeling right now. Next page. Here is the numerical example to make this model more concrete. We set R equals to 2, C equals to 0.5, and the pressure difference equals to 10. This gives us RC equals to 1, and the equation becomes Vt equals to 5 times 1 minus e to the negative t. From the table, we can see that at time 0, the volume is 0. At time 1, it increased to about 3.16. At time 2, it reaches about 4.32. This shows the land fills quickly at the beginning and then slow down as it approaches to its maximum volume. To plot our functions. So this graph shows the land volume over one bracing cycle from time 0 to t is equal to 2. The blue curve represents inspiration, where the volume increased exponentially, and the top point is t is equal to 2. The land reaches a maximum volume after that from t equals to 2 to 5. The red curve represents the expiration, where the volume decreases exponentially. The transition at t is equal to 2 is smooth, meaning the model is continuous and physically realistic. I mean, kind of. So here we explain the physical meaning of the parameters. A larger resistance R means slower airflow. The land fills and empties more slowly. And a larger compilance C means the land can hold more volume. The product RC determines how fast breathing process happens. So RC controls the speed of the system. Overall, this model connects mathematically behavior with the physiological breathing. And on the right of this page, here's our two diagrams. The diagram shows how the pressure difference drive airflow into length. When the pressure inside is lower, airflow in and the land expand. This matches our model, where pressure difference drive volume changes.
And here I'm going to talk about the importance of the lung and why we need to understand its vital functions and how it functions to make sure that people who require mechanical ventilation are basically receiving the correct calculations to simulate a real lung that they need. Lungs together work with your body's circulatory system. Each breath provides fresh oxygen, which is used by your cells to participate in a process called aerobic respiration, where your cells basically just take the oxygen and another source and other reactants to produce energy for your body to function. And that's why oxygen is such an important substance that your body needs to survive. And the way you get it is through your lungs. So for people with medical conditions that alter their ability to breathe in and out because of damaged lungs or other conditions that just decrease their function, these people need artificial ventilation so that they get the necessary oxygen their body needs. So, as we talked before, resistance of the airways ensures that you're intaking and exhaling oxygen and carbon dioxide at a steady rate. Going too fast or going too slow diminishes the efficiency of this gas exchange that happens in your lungs, and both are needed actually in a regulated amount. So also messing with the resistance can hurt the amounts that your body needs. And to maintain a steady breath, we need the correct airway resistance. And as I explained before, there's a balance that depends on this resistance. And then the other factor we talked about in the time constant is the compliance of the lung. So this is basically representing your lung tissue's ability to expand and contract, and an incorrect compliance value can affect our breathing and also determine the rate at which our lungs expand and contract. An analogy for understanding how compliance of the lung works is just blowing into a balloon. Some balloons have sturdier material, which makes it harder to blow into, and it makes it harder for the balloon to just inflate. And then some balloon material is actually very easy to blow into, and your balloon inflates at a faster rate. For people with illnesses and conditions that affect the compliance of the lung, some conditions increase the compliance and other conditions can decrease the compliance. So this is a very important factor because some people need to manage these compliance values in order to correct their breathing to the normal rate. So, for example, someone with pulmonary fibrosis has their lung compliance decreased, meaning that it's harder to inflate their lungs with air and it's harder to intake oxygen that they need. For another condition like emphysema, their lung compliance decreases due to the air sacs being stretched out, meaning that after they breathe in, it's harder for their lungs to naturally contract and push that air out, meaning that there is some air that can get trapped in. So these are two examples of why it's important to take into account of the lung compliance. And lastly, this is a connection to our the clinical implications to our ODE solution. So as we can see, for inspiration and expiration, there is a constant 1/RC that is directly multiplied to the rate of expansion and contraction of the lung. So basically, a larger RC value makes it so that the expansion and contraction are faster or slower. And yeah, these are our references, some of which we gathered our information and others are sources of our images. Thank you for listening.
Thank you.
Thank you.